Optical receiver. Here we'll study the demodulation techniques and the optical repeaters, because in the optical receiver sections we have already done with the basic part, the properties of the different optical receiver elements, that is the photodetectors. We have already done with the introductory part as to what the receiver is made up of, what are the different sub-functional units of optical receiver, and all that, those things. So we are left with the entire link. For the first thing is, for receiver part we need to know what is the demodulation technique used, and the last part is that a link, after, if it has to travel after a certain length or a distance that it can travel, if it has to travel further, then we need an optical repeater there. So what is an optical repeater, how does it work, what is its significance in the present scenario, we'll discuss it. So we start with a demodulation technique. So first, what is demodulation? It is the process by which information is extracted from the carrier after it arrives at the receiving end. So there are two important things that we conclude from this. That is, demodulation is extraction of information after it comes at the receiver, and the first thing is that the signal still has carrier, and then we get the information out of it. So this is the thing that we need to understand. Now we come to the process as such. If you look at the diagram, it consists of a modulated light input which is subjected to band pass optical filter first, then it goes to the photodetector, finally to the low pass electrical filter, and it is demodulated and we receive the electrical output. Now we'll see one by one the functions. Why band pass filter? First, the optical signal carrying the information is made to pass through an optical band pass filter. If you just notice this is optical band pass, this is not an electrical band pass filter, because optical energy here is not being converted into electrical. So it is an optical bandpass filter. Only this, that the noise or the unwanted frequencies are removed, and the exact optical signal that is required, which actually contains the information, should be put into the photodetector so that it can be correspondingly converted to electrical signal without the noise or unwanted signals that are also being carried with along with the received signal. So for removal of those unwanted frequencies or signals, this band pass optical filter is taken. And please, this is to be actually noted that the band pass filter has a center frequency which is equal to the carrier frequency. So naturally it takes in all the frequencies in and around the center frequency and discards all the frequencies away from the center frequency. So a little away from the center frequency, that is, again we'll have the range of FH to FL, that is high cutoff to low cutoff, and the entire band will be considered, which actually with the center frequency as the carrier frequency. That is how the design is made. Next, we have the filtered optical signal over here, which is subjected to the photodetector. Now what does a photodetector do? This produces an output current. This produces an output electrical current which is proportional to the time average of the instantaneous carrier intensity. So here photodetector is basically converting the entire light that is falling onto it, light energy or light signal, that is actually the carrier which is carrying the information, that is being converted over here into corresponding electrical signal. So the converted electrical signal over here contains the carrier in electrical form along with the information in the electrical form. So now it is subjected to the low pass electrical filter. So why low pass electrical filter? Because we know that the carrier is still there, and if we need to move or bring out or extract the information signal, baseband signal, which is low frequency, so that has, what we will do, we will subject the entire electrical signal to the low pass filter. In that case, the carrier being the high frequency will be rejected, and only the low frequency portion, which is the baseband signal, the information signal, will be taken in, and we'll be getting the demodulated original signal, the information signal that we require. So this is what we are saying, that the electrical signal is passed through the low pass filter to remove the high carrier frequency and obtain the original information signal. Now we come to, that is all about the demodulation technique, and the technique that was being applied, of course, if you have taken it into account, is the direct detection receiver. So the technique is direct detection. Now we come to the next important unit of a link, optical link in the receiver side, of course, because once it is transmitted, it has to be carried off continuously from one point to another point, up to a certain length maybe a fiber can take it, and the receiver may be far beyond that range. So optical repeaters are required. Okay, now optical pulses change their shape and size due to optical losses and dispersion during transmission. We know that naturally there are losses or distortions are incorporated due to travel or transmission from one place to another, and it is obviously because of losses as well as dispersion, and that changes the shape and size of the signal. Now, repeater is required to restore periodically the stream of optical pulses to their original shape and size. It amplifies the signal suitably so that the modulated light energy does not fall below the detectable level due to different losses. So, it is basically doing what? It is ensuring that the received signal at the receiver actually reaches to the receiver in a form that it can be accepted, detected, and it can be reasonably understood. So for that, it is maintaining the shape, size, that is the form of the wave shape that is traveling should be maintained. Then it should be amplified in the sense signal strength should be added so that it can travel a longer distance from that place, and it should not fall below. Well, the criteria is that it should not fall below the minimum detectable level. Now it consists of basically a receiver and a transmitter placed back to back. This is the structure that we are talking about. If you say the optical repeater, this is the optical signal through optical fiber that appears over here. This entire block is the repeater. So it consists first of a receiver. Basically the receiver is here, it is receiving. We'll do one by one. We'll study through it. Actually, if you look at this, the symbol itself says that it is some kind of a photo detector that we are placing. The light is falling onto it, and we can see that it is being converted into electrical signal here. Now this is being applied to an amplifier. The electrical signal is subjected to amplifier and shaper, when maybe the shape, the original shape and size is being maintained, and then finally being applied, this electrical signal itself is being applied to transmitter. If you look at the block over here, it is some kind of a LED symbol with diode and light emitting out of it. So it is some kind of lasers, LED or LD, that is being applied over here. So effectively, this is again electrical signal is being converted to optical, and then it is retransmitted. So in words, we will say the receiver section detects the optical signal with the help of APD, that is the photodiode we are using over here, and converts into electrical signal. Now one thing is there, that the photo detector that we are talking about in the receiver is not normally any photo detector but APD. Why? Because APD has internal gain. For photodetector section, when we have gone through, we know that only APDs have gain. So when we are talking about boosting a signal and all that, and it is in during travel that it should be boosted up, so naturally while it is receiving, it is actually providing some gain. That is why APDs are specially used in the optical repeaters. Then the amplifier and the shaping section comes in. Here the signal is then amplified and then reshaped, and then sent to the electrical as electrical input to the transmitter, and the transmitter section converts the electrical signal back to the optical signal with greater strength and retransmits it down to the optical fiber. So this is all about the process. Now in long haul optical links, it is desirable to keep the number of repeaters minimum. Why? Because the cost and complexity of the overall system increases, and secondly, the required electrical power inputs becomes difficult, especially at a location like transoceanic optical fiber links. It is very difficult to provide continuous power. Repeaters require continuous power because signal will be coming in, and then the optical detectors, the laser diodes or LEDs, everything has to be given certain bias or powers supply. So that has to be given to the optical repeater throughout. So everywhere it is very difficult because transoceanic means it is under the sea, and a repeater being placed there providing some kind of power to it will be quite a difficult process. And secondly, the complexity and cost wise also, because every optical repeater is a set of receiver, transmitter and amplifier shipper. So every repeater means the entire block. Every time it is increasing the cost and complexity, because the more number of repeaters, the probability of fault also increases, maintenance also increases, everywhere the requirements is increasing, the whole process becomes very complex. Now, with technological advancement, requirement of reshaping is eliminated partially. Why? Because near zero dispersion fibers and narrow line width lasers are available. Now, there are advancements in technology in optical communication also, especially in fibers. Fibers now have been developed which have zero dispersion. There are specific wavelengths, then they are made of specific materials with zero dispersion. So, dispersion, which is the major cause of distortion in the optical signal that is traveling down the fiber, that is eliminated because of we have zero dispersion fibers. And the lasers that are used have very narrow line width. That means there also dispersion is being limited. Line width, if it is narrow, that means it is dispersing quite less, so the dispersion is limited there also. So the entire thing is basically that reshaping, the requirement of reshaping is somewhere lost, we don't need it anymore. And earlier, because we don't need all these things and there are advancements in the technology, earlier it was the repeater spacing, that means the distance between two repeaters required was 30 kilometers. Every 30 kilometer we needed to place a repeater, but now it is 200 kilometers. So you can imagine the number of repeater requirements has reduced, and that is desirable. Now, new optical repeaters convert weak light signals directly to strong light signals, skipping the requirement of conversion from optical to electrical and back. Now, we have seen that as per the block diagram we have discussed, it consists of a receiver, the transmitter. What does it do? It does optical to electrical conversion, it is amplifying, shaping and all that, and then again uh, converting it from electrical to optical. Now this conversion was required. Why? Because it needed to be reshaped and amplified. Now when we are having zero dispersion fibers, narrow line width lasers, the reshaping requirement is gone. Amplification is only required, so we don't need it to convert it back to electrical signal. The optical signal itself can be converted to, can be boosted up, amplified. That's it. So we are basically coming down or narrowing down our requirement. We don't need an optical repeater, that means we just need an optical amplifier. So presently, actually, the present condition or present scenario is that we don't need optical repeaters. Basically, we need something that directly boosts or amplifies optical signal that is traveling. Present day, we have actually the optical amplifiers like erbium doped fiber amplifiers. We have actually the fibers are doped with certain materials, erbium. So it happens that when light is traveling across the fiber itself is a waveguide, optical waveguide. When it is traveling across it, it hits from wall to wall, and finally since the dopant they used is erbium, every time it is striking from one end to the other end, it is being amplified also. So while it is traveling, when it is supposed to lose its strength or decrease in signal strength, rather it is gaining. So effectively with distance, the strength does not drop, so the fiber itself is amplifying while it is allowing the signal to travel through it. The signal strength is amplifying actually. So the optical amplifiers like EDFA are used to amplify the pulse stream using during transmission. And the advantage is actually, or the properties we can say, is the optical amplifiers are smaller because it does not require the entire block, the transmitter, receiver and all those things, only in a simple amplifier. more, and it is more sensitive because it is optical to optical. There is no conversion factor over here, so thus it is more sensitive. It is less costly, obviously, because the number of units required is quite reduced. We don't need this transmitter receiver thing at all. We just, and even not even the shaper, just the amplifier. So out of the 4 units, we are just requiring one. So obviously the cost is decreasing, and it is greater reliability by, because here we are not use, it is not subjected to a different equipment. It is rather itself a part of the transmission. So it is more reliable. We don't need to supply other power sources and all that. The fiber itself is amplifying, so we don't need any extra powers, supply lines attached to it, so it is more reliable. And for digital transmission, the time synchronism, obviously, because once it is subjected to one kind of a block, then it goes and there is a phase delays. So those phase delays are eliminated because it is, as it is traveling along the fiber, so it is the time synchronization is also better. So these are the advantages of the optical amplifiers over optical repeaters. And these days, actually, we are preferring optical amplifiers in comparison to optical repeaters. So this is all that we needed to discuss. The review questions, obviously, what is the working of direct detection receiver that we talked about in the first slide itself, the first topic that we discussed under demodulation technique. Then what is an optical repeater, what is the need for repeater, the functional blocks of optical repeater, disadvantages of repeaters, what are optical amplifiers, and the advantages of optical fiber amplifiers. So this sums up our discussion. We'll stop here. Thank you.